Good morning and welcome back to Math 098. So for today's class, we're actually going to continue working on our distance problems, but we're actually going to see distance problems with two variables, not just one. So recall from last class, we talked about the three different scenarios involved with our distance problems, right? Where you'd add up the distances to equal total distance, where you would subtract the distances because let's say the two characters were in a race, right? So you want to find the distance that separates them. Or you'd set the distances equal to each other because one catches up to the other character, right? So we had those three different scenarios that really helped guide our interpretation of the problem, and meaning how we set up and solve the word problem. So today we're going to get into something interesting. I think it's all interesting anyways. I say interesting, but it's all interesting. So we're going to still use our charts. We're going to still use our graphic organizers, but keep in mind that this is going to be a little bit different because we're now going to include two variables, not just one. Let's take a look. Nicholas swam at a rate of 4 kilometers per hour and ran at a rate of 15 kilometers per hour for a total distance traveled of 79.5 kilometers. If he completed the race in 7.5 hours, how long did he take to complete each part of the race? So here's what I would do with this particular problem. First things first, we want to set up our chart. Rate, time, distance. I'm going to turn this just so that it's easier for me. And I'm actually going to write out here that we know we're referring to Nicholas swimming and running. So I'm going to say swim and run. Okay, that's the first thing. We set up our graphic organizer, and then let's take this apart and see what's actually happening. So first off, we know that the rate for swimming is 4 kilometers per hour. So 4, and then above rate, I'm going to write kilometers per hour, which means my time is in hours and my distance is in kilometers. Then we know that he ran at a rate of 15 kilometers per hour. So we're going to go ahead and put 15 here for run. Now check out what this says. For a total distance traveled of 79.5 kilometers. This piece right here lets us know that we can actually include one more row. So I'm going to include a total row, okay? So we know right off the bat that the total distance was 79.5 kilometers. So notice here in our distance column and total row, we can put 79.5 because we actually have that information. We're told the total distance is 79.5 kilometers. Then notice what it says. If he completed the race in 7.5 hours, he completed the entire race in 7.5 hours. So we're referring to time, and more specifically, total time. The total time it took him to swim and run was 7.5 hours. And then notice, good morning, Rachel. And then notice it says how long, so that's time, did he take to complete each part. So that means these times are probably not the same, okay? We want to figure out how long he took to complete each part. So for swimming and running, I'm going to use a different variable. I'm going to use W for swimming in the water, and I'm going to use R for running on the road. Okay, now here's the part that I want you all to recall. We know the formula for distance is rate times time. So as a reminder, just like we did in our previous problem, I'm just going to scroll up here. When we wanted to input distance for the car, we took the car's rate and we multiplied it by the car's time. So 30 times 3 plus m. That's what would go in our distance spot. For the motorcycle's distance, we would simply say, well, let's take the rate of the motorcycle and multiply it by the time of the motorcycle to get 60 m. That process will not change. So the distance Nicola swam was 4 times W, which is 4W. The distance Nicola ran was 15 times R, which is 15R, rate times time. Now, look at this chart carefully. Look at where our unknowns are. So the first thing I want to make note here is that when you have two unknowns, meaning two variables, right? Our unknowns in this case are W and R. You must have two equations. Okay, so when you have two unknowns, you must have two equations. Now, these two equations are in our chart. Let's think about this logically. Let's see what this says. W, this is the time Nicola swam. R, this is the time Nicola ran. And the total time is 7.5. Hopefully that's pretty clear to you that one of your equations is right there. The time he swam plus the time he ran is the total time, right? So here, I'm going to write down my first equation, which is W plus R is equal to 7.5. That's my first equation, but recall we need two equations. And actually, let me bring this a little closer. Much better. So for our next equation, take a look. The distance Nicola swam plus the distance Nicola ran is the total distance of 79.5. So we're actually going to identify that equation as well. So let's go ahead and write down 4W plus 15R is equal to 79.5. Now, we have already learned how to solve systems of equations. We can use a couple different approaches here. Please don't graph. Don't do that, okay? We won't be graphing these problems. We are going to either use substitution or elimination. Now, your choice, it's up to you. It doesn't matter. You're going to get the same answer whether or not you choose substitution or elimination. I personally, for problems like this where the equations are both in standard form, I love elimination, so I'm going to use that. What I'll do for all of you is I will use elimination for this first one, and then I'll use substitution for the next one, just so you could see the difference in the two styles, okay? So I want to eliminate W. So I'm going to make a little note here. Eliminate W. And if I want to eliminate W, I have a 1W and a 4W. A common multiple is 4. So I want one to be negative 4W and positive 4W. So that's my goal. Negative 4W and positive 4W. And actually, I'm going to zoom this out again, just to make it easier. So we want to eliminate W by making them negative 4W and positive 4W. So let's check it out. If I want my first coefficient here to be a negative 4, I'm going to take the entire equation and multiply by negative 4. For my second equation, I want it to be a positive 4W, and it already is. Again, if it helps, I'm just going to write that we're multiplying by 1. That's totally up to you. You don't need to indicate you're multiplying by 1, but why not? So we are going to draw the lines of distribution to show that we know exactly what we're doing. We're going to distribute. Negative 4 times W is a negative 4W. Negative 4 times R is a negative 4R. And then we have negative 4 times 7.5. When we plug that in, we get negative 30. I'm going to distribute a positive 1. We get 4W plus 15R is equal to 79.5. Now, just like before, we're going to combine these two equations. Negative 4W plus 4W, that's a 0. So we don't have to write 0 because we have our combination of terms here. Negative 4r plus 15r is 11r. And then negative 30 plus, this is a positive 79.5, negative 30 plus 79.5 is 49.5. We're going to divide both sides by 11. And you'll notice when you punch this in, 49.5 divided by 11, you should get 4.5. Now, when we see this, r is 4.5, I'm immediately going to go back to my chart. R is the time Nicola ran. So the time Nicola ran was 4.5 hours. Okay, so I'm going to make a note of that. And this is going to be part of our answer. Now, the only thing here is we need to figure out the time Nicola swam. What I would recommend is take your solution and plug it into one of the original equations. I would punch it into the one with coefficients of 1. So we have 1w plus 1r equals 7.5. That's going to be the easier equation. That's going to be much quicker in terms of finding the solution. So we know that r, the time Nicola ran, is 4.5. So we have w plus 4.5 is equal to 7.5. And now all we have to do is subtract. Once we subtract the 4.5, we find that w is equal to 3. But that should make sense. If Nicola ran 4.5 hours and it took a total of 7.5 hours, then that must mean he swam for 3 hours. So let's put our solution here. Run is 4.5 hours and swim is 3 hours. Always specify your solution and include the units to show that you know exactly what it is that you just solved for. If you were asked how far Nicola swam or how far Nicola ran, then that would actually be pretty easy to do, because consider the distance Nicola swam is just 4 times w. And w is 3. So 4 times 3 is 12. That means he swam 12 kilometers. If you want to know the distance he ran, it's 15 times r, and r is 4.5. So 15 times 4.5 is going to give us 67.5 kilometers. Okay? A nice thing to do is if you know this is 67.5 kilometers and this is 12 kilometers, when you add those two, you'll get the 79.5 kilometers. So there are many ways to kind of check to make sure that you are doing this correctly. And as always, make sense of your word problem. Make sure that your distances are positive values. You shouldn't be getting any negative values. That doesn't make sense. I don't want to see any answers that don't make sense. Just be very logical about the whole thing. I would much rather you say, the math isn't working and I don't understand what's happening, as opposed to, oh yeah, he traveled, for -3 hours. Don't do it, okay? Let's turn the page. Grover and Lucky start at the same location and drive in opposite directions, but leave at different times. When they are 320 miles apart, their combined travel time is 14 hours. If Grover drives at a rate of 20 miles per hour and Lucky drives at a rate of 25 miles per hour, how long had each been driving? So what I'd like you to do is I want to give you a few minutes. Set up this chart, just like the previous problem. Think about all of the pieces of information they're giving you. Take your time. I'm going to give you 5 minutes for this, okay? That's actually a lot of time. Go through this nice and easy, and then when you are ready, go ahead and share your answers in the chat, starting now. All right, let's take a look. So Grover and Lucky start at the same location, drive in opposite directions, right? They leave at different times. This is actually really important to note. When they are 320 miles apart, meaning one's on one end and the other's on the complete opposite end, so their total distance is 320 miles. Their combined travel time is 14 hours. So that's going to represent our total time. If Grover drives at a rate of 20 miles per hour, so 20 miles per hour, which means time is in hours and distance is in miles, and Lucky drives at a rate of 25 miles per hour, how long time had each been driving? So we don't know how long Grover was driving, so we're going to call that G. And we don't know how long Lucky had been driving, so we'll call that L. To finish off this chart, we know distance is rate times time, so 20 times G is going to be Grover's distance, and then 25 times L is going to be Lucky's distance. Notice we have two unknowns, so we need two equations. Just like before, our two equations are going to be here and here. So we are going to write G plus L. Hopefully that looks like a G. G plus L is equal to 14. There's our first equation. And then 20G, got to make sure that looks like a G. 20G plus 25L is equal to 320. Now, as promised, I'm actually going to use substitution to solve this. So what I'm going to do is I'm going to say, well, if I have G plus L is equal to 14, then I'm going to isolate one of the variables here. It doesn't really matter which one I isolate. So I'm actually going to, let's subtract L. That gives me G is equal to 14 minus L. Having said that, we are now ready to make a substitution. So I'm going to rewrite the second equation, 20G plus 25L is equal to 320, and I'm going to make this direct substitution. So where I see a G in the second equation, I'm going to replace that with 14 minus L. So that gives me 20 parentheses, and you know what? I did this also so that way I can stop writing G because it looked like my G's are just ridiculous. So I'm going to replace G with 14 minus L, and then we continue writing the equation. Plus 25L is equal to 320. Again, this is just the approach for substitution. If you've chosen not to use substitution, then great. You don't have to do this. This is just for those who want options. Notice I distributed, so 20 times 14 is 280. 20 times negative L is a negative 20L. We're going to combine like terms, and I'm going to bring over the 280 since I'm running out of room. So negative 20L plus 25L is simply 5L. And then if I subtract the 280 from both sides, we have 320 minus 280, which gives us 40. And then divide both sides by 5, and we get the L is 8. So perfect. Excellent work, Patrick. Thank you for sharing that. And Doc, you were right there. It was just the one little sign, so be super careful with that. So if we know that L is 8, and we go back to our chart, we see L refers to Lucky's time. So Lucky's time is 8 hours, right? But we also know that Grover's time plus Lucky's time is 14. So if I consider, and I'm actually going to write it over here, if I consider that G plus L, see my G's, I swear, G plus L is equal to 14, and we know that L is 8. You're making me do this again, aren't you? Then we subtract 8 from both sides, and we find that G is, in fact, 6. So this tells us that Lucky's time is 8 hours, and Grover's time, which is G, is 6 hours. So let's write that out. So Lucky is 8 hours, and Grover is 6 hours. And voila, we're done. But we are not done with distance problems related to unknowns. So we're going to continue forward. Make sure you're practicing these problems, okay? Take a look at number 7. When a plane flies with the wind, it can travel 1,960 miles in 4 hours. When the plane flies in the opposite direction, against the wind, it takes 5 hours to fly the same distance. Find the rate of the plane in still air and the rate of the wind. So with these kinds of problems, especially something that seems complicated, but I promise you it's not, the first thing we're going to do is say, well, what am I being asked to find? So I need to find the rate of the plane in still air, and I need to find the rate of the wind. And Doc, it does not matter if you're using substitution or elimination. I wanted to showcase substitution for this problem and then elimination for the previous, just to show that you can use either one. So it's up to you. Now, continuing with this idea, find the rate of the plane in still air and the rate of the wind. Well, I don't know about you, but I'm going to use P to be the rate of plane in still air. And then I'm going to use W for the rate of the wind. Okay, makes sense? Now, let's write our chart, and we are going to carefully assemble this together. So we have rate, time, distance. Again, I apologize. Okay, here's the part that trips people up. What in the heck do we write here and here? It's not like it's Grover and Lucky. It's not like it's Nicholas swimming and running. But when you think about this, what's actually happening is the plane is flying with the wind, and then the plane is flying against the wind, right? These are the two scenarios that we're referring to. So I'm actually going to write plane with wind, plane with wind, and then I'm going to write plane against wind. That's actually how I'm going to label this, because, and you'll see, it's going to make things very clear. First off, let's plug in the values that were given. When a plane flies with the wind, so we're in this row here, it can travel 1,960 miles, so we know the distance of the plane with the wind is 1,960 miles. Now you're probably thinking, wait a second, isn't that going to be rate times time? Well, my counter argument is, didn't they give you the distance? If they give you the distance, go ahead and plug that in. So it can travel 1,960 miles in 4 hours. So again, we're just talking about the plane with the wind. So we know these two spots of our chart already. So let's take care of those two. When the plane flies in the opposite direction against the wind, so here we are in this row, it takes 5 hours, so we could put 5 here, to fly the same distance. And we know the distance was 1,960. So think of it as the plane is going from its first location to its destination, and then it comes back. So it's obviously going to travel the same distance. Now, the part here that I want you to think about very logically is that we want the rate of the plane with the wind. Now check this out. P represents the rate of the plane in still air. W represents the rate of the wind. If you were flying in a plane and you're going with the wind, are you going to move slower or faster? Think about Finding Nemo. I'm almost positive you have all seen Finding Nemo because that's a fantastic movie. And do you remember the scene with the turtles who end up, like, they're swimming and then all of a sudden they get sucked into the current and they're going with the current? And you remember what happened, right? It like shoots them super fast, right? It just sends them flying in the water, right? I mean, I know this is crazy, but if you think about it like that, you'll make that connection much easier. So think of those cute little turtles who go into the current and they're going with the current and you're like, wow, they're just soaring through the water. This is the same idea, except not as cute. Right, exactly, Hannah. So it's not as cute. Now, if you're saying the plane is going with the wind, it should make sense that the plane has its own speed, and then because it hits the wind and it's moving with the wind, it actually moves faster. And what you do with those what you do with those speeds is you add them together, right? The rate of the plane, it hits the wind, and now the wind's going to help carry it forward. So you're adding those rates together. Here's how we input this into the chart. So the plane with the wind, that's going to be the rate of the plane plus the rate of the wind. And then the plane against the wind, well, that should make sense. Think about if it's really windy outside and you're walking against the wind, you're almost like leaning forward, pushing against the wind. You're like, oh my gosh, this is just totally slowing me down because this is so hard to push against this wind, which is crazy in Rochester because we get crazy wind. So you want to actually subtract the rates. So the rate of the plane is going against the wind, but the wind's not faster than the plane. If the wind is faster than the plane, what's going to happen to that plane? Okay, disaster. So the plane is going to be faster than the wind in this scenario. This is a nice scenario. This is a happy scenario. So yes, Kayla, you're exactly right. You're going to take the rate of the plane and you're going to subtract the wind because what's happening is it's just slowing it down, but it's not stopping it. Okay? So we have the rate of the plane minus the rate of the wind. Now we are ready to write our equations. You're probably thinking, but the whole thing is filled in. That's not a big deal. We've dealt with these before. If we want to write two equations, because we have two unknowns, we have to be very careful. Notice here for the plane with the wind, we can say its rate times its time is equal to distance. So in this case, your formula is going to be rate, which is P plus W, times the time, which is 4. And I like placing the 4 in front. You know, it's always helpful to put the coefficient in front. And that's equal to distance. Rate times time equals distance. So this is when the plane is going with the wind. We also need to take into account our second scenario, which is the plane going against the wind. So we have the rate times the time is equal to 1960. Perfect. Very nice. Now, don't be mad. You can distribute. You can write it as two equations. That is 4p plus 4w equals 1960. And then 5p minus 5w equals 1960. And then you can use elimination. Go for it. I'm going to show you a shortcut. Okay? Because I want you to see what you're able to do, what you're allowed to do. Again, if you don't like this, don't do it. Just distribute, use elimination, done. But for those of you who want to get creative with this, check this out. So I'm going to rewrite 4 times P plus W is equal to 1960. And instead of distributing 4, I'm actually going to divide both sides by 4. Remember, the opposite operation can be used here. So if it's 4 times this quantity, I can certainly divide by 4. If I do that, my 4's cancel, right? 4 divided by 4 is 1. And I'm left with P plus W is equal to, and then we have 1960 divided by 4, which gives us 490. I'm going to do the same thing with my second equation. So we have 5 times P minus W is equal to 1960. We're going to divide both sides by 5. 5 divided by 5 is 1. Now check out what I'm left with. And I'm going to write this directly underneath. P minus W is equal to, and let's punch in 1960 divided by 5. And that gives us 392. Take a look at both of those equations. What do you notice? I know for a fact that you said, whoa, The W's are going to cancel. Yes, they are. So what I'm going to do is I'm going to combine these two equations. These are both positive, so it's P plus P. If there was a negative, you'd actually apply the negative, right? So these are both positive. P plus P is 2P. W minus W, well, that's 0. So 0 plus 2P just stays 2P. Then we have positive 490 and a positive 392. That's going to give us, excuse me, let's do math, 882. They're both positive, so you add them. That gives us 882. Divide both sides by 2, and you get that P is equal to 882 divided by 2. Think of it as 8 divided by 2, 8 divided by 2, 2 divided by 2, digit by digit. That gives us 441. Wasn't that so quick? Now, let's think about this for a moment. P represents the rate of the plane in still air. And the rate is in terms of miles per hour. We know it is because it's hours and miles. So let's write miles per hour above the rate. So we have just found the rate of the plane. It's 441 miles per hour. I'm just going to put a note here. We are going to write our answer in a designated section. But I still need to find the rate of the wind. Now you have a couple options here. You can take the 441 and plug it into one of your original equations, or you could take the 441 and plug it into one of the equations where you've divided by the coefficient. If you feel more comfortable, you can plug it into one of the originals. But again, because I want to show you shortcuts, what I'm going to do is I'm going to plug this into the P plus W equals 490 equation. P plus W is equal to 490. We know what P is. P is 441. So essentially we're going to plug our 441 in for P, and then we're going to solve. 441 plus W, which is the rate of the wind, equals 490. We're going to subtract 441. And we're going to find that when we take 490 and subtract 441, that the wind is 49. Yes, Hannah, perfect. The wind is 49 miles per hour. And we'll go ahead and write that out. So we're going to write plane equals 441 miles per hour. And the wind is 49 miles per hour. And there you have it. So even though this seemed very complicated, we were actually able to use a few strategies that made this really, really manageable. The biggest thing is just being confident in setting up your graphic organizer. I think if you carefully dissect the word problem and you place the values exactly where they're supposed to go, you're going to be in great shape and you'll have no issues moving, flowing through this kind of a problem. Okay, but of course, it takes practice. Good. We're going to turn the page and we're going to do one more problem. A boat's crew rowed 30 kilometers downstream with the current in 3 hours. The return trip upstream against the current covered the same distance but took 5 hours. Find the crew's rowing rate in still water and the rate of the current. So we start by saying, what am I trying to find? So we want to find the crew's rowing rate in still water, and we want the rate of the current. And when you think of current, think of that water. So I'm going to call C the rate of the crew, right, in still water. This is without any currents. And then the rate of the current, I don't want to use C again. I'm going to use W for water. So the rate of the current. And of course, we're referring to the water. Okay, we're going to set up our chart just like we did before. So we have rate, time, distance, And we're going to figure out how to actually label this. So think about this scenario. So like before, we had the plane with the wind and we had the plane against the wind. In this case, we're talking about a boat's crew rowing with the current and then rowing against the current. So I'm going to say crew with current, crew against current. That's how I'm going to label it. The crew with the current and the crew against the current. So now let's plug in our values exactly where they belong. A boat's crew rowed 30 kilometers downstream with the current. The crew with the current, 30 kilometers downstream, that's distance, right? And it took 3 hours. Perfect. I'm placing information exactly where it goes. If your time is in hours and your distance is in kilometers, then this is going to be kilometers per hour for your rate. And it's always helpful to label it. So we've taken care of these two pieces of information. The return trip upstream against the current covered the same distance, right? Because it's a return trip, but it took 5 hours. Okay, so far so good. Now all we have left is to write out what the rate should be. Again, notice here it says the crew with the current and then the crew against the current, where C represents the rate of the crew in still water and W represents the rate of the current, which is the water. That's why I use the W. So the crew with the current is going to be C plus W, the crew plus the water. And then the crew against the current is going to be C minus W. Now that our chart is completely filled out, we can go through the motions we went through for problem 7. And again, I want to go through the path of least resistance. So we're first going to write out our equations. So we have 3 times C plus W is equal to 30. Rate times time equals distance. And then 5 times C minus W is equal to 30. Again, rate times time equals distance. The shortcut that we learned is that if we divided both sides by 3, for instance, we divide by 3, we get C plus W is equal to 10 without a coefficient. It actually makes it a lot easier. If we take the second equation, we divide by 5. Notice the 5's cancel. We're left with C minus W is equal to 6. By dividing out these coefficients, we have our 2 equations in our system, and it becomes incredibly easy to solve. So these are both positive C's, so we have C plus C, which is 2C. The W's cancel, and it leaves us with 10 plus 6. They're both positive, so 10 plus 6 is 16. Divide by 2, and you get that C is 8. Yes, excellent, Hannah. That's perfect. So I'm guessing that Hannah took this C is equal to 8 and plugged it into C plus W is equal to 10. That's one of the easier equations. It's the one that's most straightforward. If we know C plus W is equal to 10 and we know that C is 8, all we have to do is solve for W. We subtract 8 on both sides and we get that W is equal to 2. So for our answer, we're going to say the cruise rate is 8 kilometers per hour. And then the rate of the current, so the current's rate is going to be 2 kilometers per hour. Again, the water should not be faster than the crew. Otherwise, the crew is going nowhere. What I'd like you to do in your notes below is write down any key notes on distance or motion problems that you need to remember as you solve them. I want you to really think about information to put in that little spot in your own notes. You know, maybe it's things of be careful to read the word problem word for word. Be careful to determine if you need 1 variable or 2 variables. Be careful if you need a total row or not. You know, the things that you were working on in this section that you want to say, don't forget. Okay, this is good practice. Write down in this section your don't forgets. Okay? On that note, I kept you a minute too long. Sorry about that. I'll see you all tomorrow. We're in week 9. We are making moves. I'll see you all tomorrow. Bye, everyone.